Hey YouTube, what's up, it's Link? Welcome back to another episode of Coding Session. I know it's been a while. These past few months have been wild for me, between work and family. And I got into an altercation with a certain individual regarding a open source project that I was involved with. If you wish to read that open statement, you can go to my software development portfolio, Slinksoft. But I'm okay now. I've moved past it. And if you want to read into that and my reasoning why and what project was, you can check that out. But yeah, I haven't been doing much. I haven't really been working on any projects. I have been doing some commits to some projects lately, if you checked out my GitHub recently, but I feel like I haven't done too much. So here is another episode of Coding Session. And this problem in particular caught my interest because it relates to a project that I was working on during my final semester in college. If you remember back in the depth first search video, a couple episodes back, probably a handful of episodes back, I showcased part of that project. And this problem kind of relates to that in a sense where you're going ahead and traversing a graph and building up a path with neighboring nodes. And building up that collection of paths and returning it. If you want to check out that video, I explain a bit more about the project itself and what we use the depth first search algorithm for. A few episodes back, title should be depth first search showcase of a project or something along those lines if you want to check that out. But yeah, all paths from source to target given a directed acyclic. Wow, I can't pronounce tonight. I just don't see that word often. Graph, DAG, of n nodes labeled from 0 to n-1. Find all possible paths from node 0 to node n-1 and return them in any order. So basically what the problem wants us to do is it wants us to build a collection of paths, and each path is going to start at 0, which is the default. That's the start of the graph, and traverses every possible path within the graph to that end. So pretty much, see the 0, 1, 2, 3, pretty much every single possible path from 0 to other neighboring nodes. And we're going to use a depth first search algorithm for that. I kind of already spoiled that. So let's do it. I'm using C#. It's my favorite language. You can use other languages if you want. Very similar. Solution should be similar. So we're going to create an iList of integers result with a new list iList int. Okay, and we're going to create a list of integers for our path equals the new list int, and we're gonna just initialize that with some data. Let's put 0, so it's ready for our depth first search algorithm. And for our base case, if the graph length is equal to 0, return result just the way it is, because, well, there is no graph. So return result. Okay. And now in this comment, run DFS. This is where we're going to run our depth first search algorithm. And we're going to return the result as that finale. So let us write our depth first search algorithm so we can complete this solution. We're going to create it, give it a bool type, a private bool, depth first search. And we're going to create some input parameters, some arguments. So matrix, integer, or 2D array, graph, iList, int. And this is pretty much going to be similar to these two, since we're going to pass them in our depth first search algorithm. So therefore, we're just going to it's going to be a little bit ambiguous, but we're going to keep the name the same, just so it's a little bit less confusing. We don't get mixed up with our variables, but of course, it's going to be grabbing these. Obviously, this is a local variable, not the instance. It's within this method itself of ilist int. Okay. List int integers of path, and finally int index. Okay, so of course we always start with the base case. In this case, since we're traversing the graph from 0 all the way down to whatever n it could be, as long as the path starts from 0 and ends in n minus 1, simply our base case is going to be if our index is equal to graph that length minus 1, meaning it's reached that n minus 1 from 0 to n minus 1, that n part of that path, return true so we don't get to a stack overflow. And going back on the stack and building our paths. So towards the end of the graph, that's it. We're going to stop, keep going back up the stack. And we're going to create a for each of integer neighbor. We're going to call that n in graph index. Now you notice when I said neighboring nodes at the beginning of the video, it's pretty much what we're doing, grabbing all those neighboring nodes and going ahead, collect them. So we're building each path from 0 to whatever its neighboring nodes is, and continuing to build up that path and going through a depth first search algorithm until we reach the end of that specific path. And that's how we know we got a path from 0 to n minus 1. We're going to add that to our list or collection of paths. I don't know why I put it equal here. I'm very tired. This is the only time I only have time to do an episode now, because within the next few days it's going to be really busy at work and family, so yeah. So I apologize if I'm a little shaky. So path.add, building our paths with all the neighboring nodes, and if depth first search, which is going to be, here's the recursion, here's where the recursion starts, graph result path and neighbor, let's put that and that index, result dot add path, and convert that to list form, and we got that path. As we reach that end, it returns true, hits our base case, and goes up the stack. Finally, path.remove that, and this is going to clean up that path argument, the path variable, so we are ready for the next path to find. Of course, depth first search algorithm, it dives down as far as it can before traversing back up and traversing for other possible paths. Again, if you want more in-depth explanation of depth first search, since we already covered it in an episode relating to that project I worked on in my final semester during college. It's a few episodes back, but the title should contain depth first search if you want to learn more. And viewing it in a real world scenario example, in a sense. Not just something solving a problem theory-wise, but actually using it for an actual application. Okay? And of course, obviously, if we haven't reached that end of our base case, we simply just want to return false at the end. And that is our depth first search algorithm. So if we call it here, DFS, graph, result, path, 0, start index. Okay, so let me make sure everything's good. I might have messed something up because I'm so tired, but let's run the code and see. There we go. Accepted. For the first test case, let's see if all other test cases pass. There we go. Success. Ran 260 ms faster than 68.21% of C# submissions. That's pretty good, better than I thought. But yeah, I have experience with using depth first search in this sort of scenario when it comes to traversing a graph and finding many paths using the neighboring nodes. It's pretty much all graph theory in a sense. And I did learn some basic graph theory for that project I was working on my final semester. Had to, in order to kind of understand what was going on when we were traversing these network topologies. But yeah, that is, I already forgot the name of the problem. The DAG all paths from source to target problem on LeetCode using the depth first search algorithm. Thank you guys for watching. If there's something that is unclear, you need a better explanation on, please leave a comment down below. Can't even speak. And I'll try to help you out the best I can. So that's pretty much it. Thank you guys for watching. Have a nice day.